Hello everyone, welcome to the Math 371 Coronavirus Edition. I hope that you all are healthy and well at home. Over the course of the next 2 weeks, I'm going to be creating a series of videos that you will watch and take notes over. You'll then either photograph your notes or scan them in and then upload them on Moodle. I know this is not ideal, but I thought that the flexibility given by watching a video would outweigh any benefits of having a class time via Zoom. I'm going to try and have some office hours online via Zoom just for this class. I will do what I can, but as you know, we're all kind of having a rough time trying to transition to online classes. You might be wondering, why am I so adamant about getting the material in? There are a variety of reasons, but I think that linear algebra is one of the most important classes that you will encounter during your undergraduate career, and I don't want to fall behind because of it. The material over the next couple days will help solidify some things that you already know, and so I hope that you find it not too difficult to grasp via video. Obviously, give me any feedback you have. I'm going to create a forum for each topic or day in class, and so if you have questions about the lecture, please post your questions on that forum in Moodle. Moodle will be your guide during this time, but you can email me if you cannot find your answer on Moodle. All right, a couple reminders going forward. You will have your Pearson homework due on Friday, and I've already discussed taking notes and copying them. That helps me know that you're keeping up to speed during this time. All right, so today we're going to learn about Cramer's rule. This is section 3.3. I apologize in advance for my handwriting. The stylus is not the easiest thing to write with. Okay, so let's suppose we have a matrix A, and it's a n by n matrix. And it's invertible. Okay. Is there a nice way to write the solutions of AX equals B? So we know that we could multiply both sides of the equation by A inverse. So we know that A inverse times A times X, well, that's just equal to X, but it's also equal to A inverse B. We could do it this way, but is there another way? So today is a day where we're going to just practice properties of the determinant and solving linear systems. We have one way of doing it, and now we're going to learn another way so that we really get the hang of computing with determinants. Okay. In order to find this other way, we're going to need a definition. So let's call our solution X. This is our solution. And we're going to define the matrix A times I sub I of X to be the following. This is going to be the matrix A times a new matrix. So what is this new matrix? Well, it's the identity matrix where we replace the ith column by x. Okay, and we're going to multiply this out. So what it is equal to is a new matrix where these are the columns. And we're going to call these A1, where A1 is the first column of the matrix A, and then we have column I replaced by the vector B, and AN. So what we're getting is the matrix A, where we've replaced the ith column by the vector B. So this is the matrix A, with ith column replaced by the vector B. All right, so we're going to take the determinant of both sides of this equation. So after all that work, we know that A times the identity matrix with the ith row replaced by x is the same as the matrix where the ith column, A of A, is replaced by the vector B. And we take the determinant of both sides, and that yields the determinant of A times the determinant of the matrix II of x is the determinant of this matrix here on the right. Okay, so bear with me and we're almost there. We know that this piece right here determinant is just equal to xi. That is the ith element in the vector x. And so what this tells us is that xi is equal to the determinant of this matrix on the right over the determinant of A. So what does this tell us? What it tells us is that we can compute the solutions using determinants. So instead of inverting the matrix, we can actually just use determinants. And that's a really interesting property of determinants that you might not have guessed. This property, or theorem, is called Cramer's rule. And I'm going to write that now. So Cramer's rule tells us exactly what you just copied down. It tells us that if A is an invertible n by n matrix, and we want to solve the equation ax equals b, where b is a vector in the real numbers raised to the nth power, then this tells us that the vector x, which is x1 to xn, we know what these entries are. xi is equal to the determinant of ai of b over the determinant of a. And this is what we call Cramer's rule. And we're going to use this to solve the following example. So in the following example, we want to use Cramer's rule to solve the following linear system. So this vector on the right is our vector b, and this matrix on the left is our matrix A. And we need to compute a variety of things to compute the solution. So what I want us to do is I want you to try doing this, and I want you to write down what is the matrix A1 of B, A2 of B, and A3 of B. So that's where we replace the first column or the second column or the third column of A by the vector B. So pause the video and write down what those matrices are, and I'll tell you what the answer is in just a second. Okay, now that you've had that opportunity, you can pretty easily see that these are these matrices that you obtain by replacing one of the columns of A by the vector B. So what we need to do is we need to calculate the determinants of these four matrices. We need to compute the determinant of A, the determinant of each of these matrices on the left. And so what I want you to do is to take a moment to work in your notes, might take you more than a minute, and calculate each of these determinants. To remind you how we calculate them, this will be an important skill to learn for the next test, and it's really intricately related to abstract algebra, a class I'll be teaching in the fall. So pause the video and take a few minutes to calculate these determinants, and then I'll write down what they are. Alright, after all that work, you should have calculated that the determinant of A1 of B is negative 2, the determinant of A2 of B is negative 22, the determinant of A3 of B is negative 3, and the determinant of A is negative 8. And so what this tells us is that our solution to our equation, x1, is negative 2 over negative 8, which is 1/4. Our second term of our solution is negative 22 over negative 8, which is 11/4. And last but not least, x3 is negative 3 over 8, or 3/8. And so that means that the unique solution to our equation is 1/4, 11/4, 3/8. And you were able to calculate this using determinants. Alright, so let's turn our attention to using Cramer's rule to actually calculate the inverse of a matrix. So, using Cramer's rule, for computing A inverse. So this is going to continue to show you the connections between determinants and inverses. So how do we possibly do this? Well, let's think about what finding the inverse actually is. So, question, what is the inverse? The inverse is a matrix that when I multiply it by A, I get the identity matrix. So I want to find the jth column of A inverse. And let's call that X. What do we observe about A times X? Well, if you think about it, when you think about, you take the row of I and you dot it with the column of A inverse, you should get one of the vectors EJ. This is the vector of all zeros with a 1 in the jth row. Alright, so what can we do? Well, we can use Cramer's rule. So what does Cramer's rule tell us? Well, Cramer's rule tells us that x sub I should be equal to the determinant of A in the denominator and the determinant of AI of EJ. Well, what is this? This right here is the matrix A where you've replaced the ith row by EJ. And if you look at that closely and compute the determinant where you expand on the ith column, you will find the determinant of that matrix is actually just equal to something you've seen before. And in fact, this is what we call the CJI cofactor. And so what you obtain is actually a formula for the entire inverse. You find that everything is divided by the determinant of A, and you multiply that by a matrix, which is a little bit funny. You see that the notation for the row and the column have been flipped. And so what you find is that you can calculate a bunch of determinants and get a formula for the inverse. And we call this matrix on the right the adjugate. So I'm going to give you an example where you're going to compute the determinant using this form of Cramer's rule. It's going to take you some time, but then I'll do a little bit of it and then, show you the answer. And your work will be in your notes. So let's do an example. We want to we said that A is equal to 1, 0, 2, negative 1, 2, 0, 2, 1, 4, and we want to find A inverse using this form of Cramer's rule. The good news is, although we have to take a lot of determinants, they're all 2 by 2 determinants except for the determinant of A. So what you're going to need to do is you're going to need to write down several matrices and compute the determinants, but most of them are going to be pretty easy. So what I want you to do is first figure out what's the determinant of A, and then compute these are their cofactors, which will require you to know determinants of some smaller submatrices. Okay, at this point, stop the video and compute all of these necessary determinants. One of them will be a 3 by 3 determinant, but the others are all 2 by 2. And don't forget the factor of -1 to the I plus j. Alright, pause the video now and give it a shot. Alright, you should have gotten these numbers for your determinants or your cofactors. Remember, the cofactor has a term where you multiply a determinant by -1 to the I plus j. Alright, so what this tells us then is our inverse is 1 over -2 times this matrix right here. So remember, it gets flipped from what you would normally expect it to be. And we should get the following as our determinant. Alright, so that was a fair amount of work, but if you don't like row reducing, you might prefer this. And so what you see now is how we can use determinants to calculate the inverse of a matrix using Cramer's rule. Alright, so the MyMathLab will have some examples for you to do there, and mostly this is about implementing a routine, a formula, and the important part is getting a sense of where it comes from. Alright, so to finish today, we're going to talk about certain computations of areas of parallelograms or parallel pipets using determinants. So if you saw Calc 3, you saw some equations to compute the volume of a parallel pipette or a parallelogram using some formulas that were like a determinant. So let's take a look here. So area via determinant. This is one of the most important pieces of the determinant, is understanding that it relates to area or volume. So we want to find the area of a certain parallelogram. So find the area of the parallelogram with the following 4 points. Okay, so we can graph to see what this looks like. So we have a point there, we have a point up here, we have a point here, and we have a point right here. So this parallelogram looks something like this. And we want to compute the volume. So we see that this parallelogram is actually given by 2 vectors. It's given by a vector that goes 1 to the left, and it's given by a vector that goes over by 2 and up by 3. And then the other 2 pieces of the parallelogram just fill in those 2. Okay, we want to calculate this area. It turns out the area of this parallelogram should just be the determinant of the matrix given by those 2 vectors, but then we take the absolute value. So if we take this determinant, what we get is we get a determinant of -3, and we take the absolute value, and so the area is actually 3. Now, why does this work, though? We're going to investigate why that's true with parallelograms, and then we're just going to say it's true for parallelepipeds, which are a three-dimensional version of the parallelogram. So let's see why this works. So we're going to start with the easiest case. The easiest case is where you have two vectors that are perpendicular. So we look at the vector a0 and the vector 0d. We get two vectors, and so we see here that the area here is clearly equal to A times D, because it is a rectangle. So in order to generalize this, we need to kind of think about the following situation. So let's imagine we have 0 and we have the vector a1. And we have this parallel line. This is the vector a2. These are parallel lines here. This is the line L, and this is the line where we've translated L by the vector a2. So the question, though, is, well, what is this vector right here in blue? Well, that vector in blue is merely a2 plus some multiple of a1. I don't know what that multiple is, but it is some multiple of it. And so I see that the area in blue is merely equal to the determinant of the matrix A1 and A2 plus a constant times A1, because it's a rectangle, and we already said that it works for rectangles. However, if I look at my original parallelogram in red, I see that the area of the red parallelogram is the same as the area of the blue parallelogram, because these are parallelograms with the same base but different heights. So we see that this is equal to the same determinant up there. But what do we know about determinants? Well, I can add a scalar multiple of one row or column to another row or column and keep the same determinant. So what I will do is I will add -c times row times column 1 to column 2. So add -c times column 1 to column 2. And this does not change the determinant. We learned this a couple of classes ago when we learned about how do basic row or column operations affect the determinant. So now you sort of see an argument for why, if I need to find the area of a parallelogram, I just find the vectors that give you the sides of that parallelogram and then compute the determinant and take the absolute value. Flipping the order of the vectors merely flips the sign of my determinant by -1, so taking the absolute value does, fixes that. All right, so one last example is the example of the parallelepiped. And so if I have a parallelepiped, and let's say I have 3 vectors that give 3 adjacent sides, and so let's call these vectors u, v, and w. Then this tells me that the volume of the parallelepiped is the absolute value of the determinant of the 3 by 3 matrix given by those 3 vectors. And we'll work on an example so you can determine what these sides are. So we're going to do an example, and you're going to see how it works. We're going to find the volume of the parallelepiped, which is a real word, by the way, with one vertex at the origin and 3 adjacent vertices at the following 3 points. Okay, and now we need to find the determinant. So we need to find our vectors u, v, and w. And the vectors are the vectors we get from starting at the vertex, the origin, and going to these 3 different adjacent vertices. And so in this case, it gives us 3 pretty easy vectors. It won't always be so easy, but today it is. And this should tell us that the volume is the determinant of the following 3 by 3 matrix, where we just put each vector as a column. So I want you to pause the video now and compute the determinant to see what the volume is equal to. Alright, you've had your chance, and so it should be that the volume is 23. So now you know how to calculate volumes of parallelepipeds and areas of parallelograms. Let me know if you have any questions, and be sure to post them on the forum. Alright, see you Thursday. Bye.